Alright, it's time to get serious and learn about the Knuth-Morris-Pratt or so-called KMP algorithm. This algorithm was designed to solve the previous problem, which was string matching. Given two strings, we have to find the occurrences of the second string as a substring in the first one. I've taken here another example, in which you can see that we are looking for the string onions inside this string. And it appears only once, which is here. Its starting index is 3, so this is why we return the array 3. Now, do you remember the brute force approach that we have used in the previous lesson? I mean, the first brute force approach. It was pretty simple. We have tried out each and every substring of length m, which is the length of the pattern string, and then compared that substring to the pattern string. If they are equal, we pushed the starting index into the array, and in the end returned it. That solution was big O of n crossed m, and is indeed the brute force approach that Knuth, Morris, and Pratt started with. So just as a reminder of how important brute force approaches are, even the best of the best use them all the time. But these guys took it to the next level, and they made an awesome optimization, which, trust me, it is super hard to come up with. I wasn't able, and none of my students were, so don't worry about it. The purpose here is just to understand the optimization, how it works, what happens behind the scenes, and of course when to use it. The first substring that we have tried out in that brute force approach was of course the one starting at index 0. So it was this one. Now, what have we done? Of course, we compared onioni to onions, and we've seen that the first, second, third, fourth, and fifth characters are the same in both, but here these are different. So after concluding that this substring is not equal to the pattern string, what have we done? Of course, we moved to the next substring and tried that one out. Then moved to the next substring and tried that one out, and so on and so forth. These guys were upset that we had to try out some substrings which are obviously not going to be equal to the pattern string. For example, why even bother trying out this substring when it is pretty clear that the first character is different than the first one in the pattern string? Also, why trying out this substring when it is pretty clear that its first character is different than the first character in the pattern string? They thought that if we already tried out the first substring, so we have already iterated through a bunch of characters until we have found the first two correspondent different characters, maybe we can use the information we have gathered along the way, so basically the values of these characters, in order to make sure that in the future we are not going to try out a substring which is definitely going to be not equal to the pattern string. When we tried out the first substring, we have basically iterated through the first 6 characters, so now we know their values, and all the other characters in the text string weren't discovered yet. So I'm just going to note them by stars, just to know that I still don't know their values. I haven't iterated through them yet. I have no information about them. Only knowing these 6 characters, can I tell if some of the substrings that my brute force approach is going to try out next will not be equal to the pattern string? And the answer is yes. For example, I know for sure that this substring is not going to be a good one, even without knowing the value of this character, because I know that the first character is n, which is different than o. There is no point in trying out the substring. This is also true for the next substring that my brute force approach is going to try out, which is this one. Without knowing the values of these two characters, because the first character is I know for sure that this substring is not going to be equal to the pattern one. But if we take a look at the next substring that our brute force approach is going to try out, which is this one, this substring has the potential to be equal to the pattern string. And why is that? Because the only 3 characters that I know, that I've iterated through, are indeed equal to the first 3 characters of the pattern string. So this prefix of length 3 is indeed equal to these 3 characters. My point is that after we check a substring, some of the next substrings that we are going to check will share a couple of characters with this substring. For example, this substring shares 5 characters with the previous ones. So its prefix of length 5 is actually equal to the suffix of length 5 of the previous substring. And because this suffix is not also a prefix in the pattern string, we know for sure there is no point in checking this substring out. Also, for this substring, if we were to check this substring, it is going to share 4 characters with the first substring that we have tried out. So its prefix of length 4 is going to be equal to the suffix of length 4 of the first substring. And because this suffix is not also a prefix in the pattern string, there is no point in checking out this substring. But if we try out this substring, its prefix of length 3 is also a suffix of length 3 in the first substring. And because this suffix of length 3 is actually also a prefix in the pattern string, then this substring is the first one that really has potential, and we should check it out. So the observation Knuth-Morris and Pratt made is that after finishing trying out one substring, there is no point in trying out each and every next substring in chronological order, but instead find out what is the longest suffix of this substring, which is also a prefix in the pattern string. For example, if we take a look at the suffixes of this substring, oni-oni, its longest suffix is the substring itself, oni-oni. Oni-oni is not a prefix in the pattern string. Then we move on. Another suffix of this substring is ni-oni, which, as you can see, is not a prefix here. So we move on and try out the next one. The next suffix is this one, ioni, which is not a prefix here, so we move on. And the next suffix here is oni, which is indeed a prefix in the pattern string. So we have found the longest suffix, which is also a prefix in the pattern string. What we are going to do next is check if the substring that starts here is indeed equal to the pattern string. We know, of course, that the first 3 characters are equal to the first 3 characters in the pattern string, but we need to check the next ones. So I'm going to start from this character and compare it to this character. In the original string, this character was O, which is equal to the next character here. So what I have so far is a prefix of length 4 in the pattern string, which is also equal to our current substring. So we can move on and now compare this character to the next one in the pattern string. This character in the original string was N. It is equal with the next character here, so now we have a prefix of length 5 of the pattern string, which is equal to our current substring. So we can move on and check this new character with the next character in the pattern string. This character was S in the original string, which is indeed equal to the next character here. So now we have a prefix of length 6, which is also the length of the pattern string, which is equal to our current substring. So we have found our first solution. We are going to push the start index 3 in our answer array. And what we are going to do next is, of course, look for other solutions. So now our current substring is here, onions, and this is the pattern string. And let's see if we can use again that line of thought to figure out what is the substring that is most probably to be equal to the pattern string. Again, some of my next substrings are going to share some characters with my current substring. And again, those characters are going to find a suffix in the current substring, for example here. And in order for the substring to be equal to the pattern string, this suffix has to be also a prefix in the pattern string. So I will do the same thing and find out what is the longest suffix of my current substring, which is also a prefix in the pattern one. And, of course, the longest suffix is onions, which is equal to onions, but I'm not gonna take it into account because it is the same substring. Then, the next suffix is this one, which is obviously not a prefix here, so it's not good. The next suffix is this one, not a prefix here, not good. This one, not a prefix. This one, not a prefix. And the last character, which is also not a prefix. So what is the conclusion that we can take from here? The conclusion is that there is no point in trying out a substring which starts on one of these characters. So the next subarray that I'm going to try out next is the one that starts on this character, because these characters are yet unknown, and of course they can have the potential to give me a substring equal to the pattern string. In this scenario it won't happen, of course, because we only have 2 characters left, but imagine there were at least 6 characters left. Maybe we have the string onions there. To be honest, I don't remember what were the last 2 characters, but doesn't matter. Let's suppose for the sake of this example they were O and N. What's gonna happen next? Well, because the longest suffix of the current substring, which is also a prefix here, has length 0, so there is none of them, we can conclude that we have to start fresh, and this first character is going to be compared to the first character here. O equals O, nice. N equals N, nice. But of course, when I try to compare I with the next character doesn't exist, so we finish here the algorithm. Now, to talk about the algorithm, as you can see, we always have a possible starting position for the string that we are going to check, and also a position here. As long as the characters are equal, we just increment these 2 pointers. So these 2 are equal, we are going to move to the next one and the next one, equal, next one, equal, next one, also equal, next one, also equal, next one, and they are not equal. Now, it is the time where we have to find the longest suffix, which is also a prefix. Of course, this can be done easily with a brute force approach, but this is not the point, because even if, let's say, we find the longest suffix in big O of m, our time complexity will still be big O of n crossed m. Once we have found the 2 correspondent distinct characters, we are going to actually move 1 step back and keep only the characters that are equal. So in this case, we are moving 1 step back and only keep onion, which is also equal to onion here. And what we are going to do next is actually find the longest suffix of this substring, which is a prefix here. In this example, it is on. And we do this because this information is actually easier to pre-compute. We are going to first pre-compute an array, which we will name LSP, which stands for longest suffix prefix, based only on the pattern string. Let's write the definition of the array. LSP of I is equal to the longest suffix prefix of the substring, which is also a prefix, as you can see, pattern 0i, besides the substring itself. Let's take this example onions and see what I mean by that. I will take each and every prefix of the pattern string and compute the length of the longest suffix of that prefix, which is also a prefix of that prefix, right? So, for example, when I want to compute LSP of 0, I need to take a look at pattern of 0 and 0. So, the substring containing only the first character. This is O. As you can see, LSP of 0 equals 0. Why is that? Well, what are the suffixes in this string? Of course, we have only one of them, which is O, which is obviously also a prefix, but we are not going to take it into account. That's why I said besides pattern of 0 and I, because no matter what is the string that you take, of course, the whole string is a suffix and a prefix, so the answer would always be the length of the substring, right? For example, on, yeah, it is a suffix and a prefix, so this one should be 2, here should be 3, and it's super straightforward. But it doesn't help us, as you have seen in the previous example. We want to find this longest suffix prefix, which is not the string itself. So here we don't have any other suffixes and prefixes, so LSP is 0. Now, pattern of 0 and 1, we have the substring on, and the suffix is n, which as you can see is not also a prefix. The prefix of length 1 is O, so we don't have any, again this value of 0. Then, the next pattern of 0 and 2 is O and I. The first suffix is I, which is not a prefix. Then another suffix is ni, which is not a prefix. The prefix of length 2 is on. So we have none, and LSP of 2 equals 0. Now for pattern of 0 and 3, we have onio. So we have this suffix, which as you can see is also a prefix. So we have a length 1 already, and if we try out the other ones, we have this suffix io, which is not a prefix. The prefix of length 2 is on. We have the suffix nio, which is unfortunately not a prefix. So the longest one was of length 1. This is why LSP of 3 equals 1. In the next prefix, onion, the LSP is 2. Why is that? Because we have this suffix of length 2, which as you can see is also a prefix. If you try the longer ones, for example, ION, this is not a prefix, and neither is NION. It is not equal to ONIO, so LSP of 4 equals 2. And for the last prefix, which is the whole substring, onions, we have no suffix, which is also a prefix, so the LSP equals 0. We will see a little bit later how this array is going to be computed, but first of all, let's take another example where we also write the values of the SLP array and see how the algorithm works. And let's take this example. We have the text string, the pattern string is still onions, and the SLP array is the one that we have previously computed. Now, what do? We start with a pointer here, and of course we start comparing from here. And we start comparing the characters, and as long as they are equal, we increment our pointers. So O and O, everything good, N and N, I and I, O and O, N and N afterwards, and then we find the first two not equal characters, which are I and S. At this point, we know that the substring that starts here is not going to be a valid one, but we also know what is the longest prefix of this substring, which is also a prefix here. So we will move with our pointer one step back. The pointer is going to end up here. And what we know is that this prefix is equal to a prefix in the pattern string. What we should do now is find the longest suffix of this substring, which is also a prefix here. And here comes the nice part. Because we know this substring is equal to a prefix in the pattern string, we can get the information we want from the LSP array. Onion is the substring pattern of 0 and 4. So we take a look at LSP of 4 and we see that its value is 2. This means that the suffix of length 2 from the pattern string, which is ON, is also a prefix. But also, because this substring is equal to this one, we know that this suffix is also a suffix here. So what we know for now is that the suffix of length 2 from the previous substring is also a prefix of length 2 in the pattern substring. This means there is some potential with this substring, but we have to move on and check all the other characters. And so we will do I equals I, move on, O equals O, move on, N equals N, move on, and S equals S. So the substring that starts in this position, which is onions, is equal to our pattern string. We will push the starting index to our answer, so the starting index is 3. And then, in order to try out the next substring, we need to know what is the longest suffix from this substring, which is also a prefix here. And because we know these two are equal, I am going to look at LSP of 5 in order to get the length of that suffix. And as you can see, its length is 0, which means no suffix from this substring is also a prefix here. So what am I going to do? Well, no point of trying out a substring that starts here, so I am going to move my pointer here, and also because the LSP was 0, I'm going to start with my first character in the pattern string. I start comparing the characters, O equals O, N, N, I, O, O, N, N, so the pointer will be here, and this pointer will be here, and I see that these are my first two characters which are not equal. So I know this substring is not a valid one, but what I also know is the longest prefix of this substring, which is also a prefix here, and these are onion. So what am I gonna do? In order to try out the next possible valid substring, I need to know the longest suffix from this substring onion, which is also a prefix here. And because these two are equal, I actually need to know the longest suffix from this substring in pattern, which is also a prefix. And of course I know this value, it is LSP of 4, which equals 2. And indeed, the suffix of length 2, which is also the suffix here, will be equal to the prefix here. So, if I know this information, that this suffix here is going to be equal to this prefix here, what I need to do is try out the next characters to see if this substring is indeed a good one. So I'm going to move my pointer here and here. Compare the characters, I see that all of them are equal, so my pointer is going to eventually be here, and this one is going to be here. I find that this substring, onions, is also equal to the pattern string, so I'm going to push its starting index into my answer array, and the starting index is 12. So I push 12 into my solution. What am I going to do next? Find out what is the longest suffix, which is also a prefix here. So I need LSP of 5, which is 0, so there is none. No point in trying out a substring that starts in one of these characters, so the only substring that I should try out is on the next character, which we don't have a next character, so the algorithm finishes. And this is it, guys. I hope that you got now a good idea of how the Knuth-Morris-Pratt algorithm works after having computed these values. And of course, what we are going to do now is take a look at the code, first how to compute the array LSP, and then how to use it in order to find the answer to our problem. First of all, let's take a look at some general example. Let's say this is our string pattern of length m. We don't care about the values of the characters, they could be anything. We care about the mechanics when computing LSP of some position I. Let's say that this was LSP of I. This suffix of length LSP of I is also a prefix. Well, if this happens and these two are equal, obviously these prefixes of them, this one and this one, of length LSP of I minus 1 are also going to be equal. But as you can see, this is a suffix that ends in I minus 1 and is also a prefix. So it might be LSP of I minus 1. The natural thing to do when trying to compute LSP of I is to first take a look at LSP of I minus 1. So let's erase these two for now. Let's suppose that this is LSP of I minus 1. So this is a suffix and it is also a prefix, both of them of length LSP of I minus 1. In the best case scenario, I will be able to extend this prefix and this suffix by one character. So, if these two are equal, let's suppose they are both equal to A for the sake of this example. If they are equal and also these two substrings are equal, of course, this one containing the new character A and this one also containing the new character A is going to be our LSP of I. So if these two characters are equal, LSP of I, as you can see, equals LSP of I minus 1 plus 1. But they won't always be equal. Let's erase this for now. And let's suppose that this character was a B, which means that LSP of I won't be equal anymore to LSP of I minus 1 plus 1, but will be something less. Let's suppose this is LSP of I. This one, which is also a prefix here. So these two have length LSP of I. This means that the last character of this prefix is a B, so this should be a B, and also these two substrings, this one without the B and also this one without the B, should be equal. The beautiful part here is that also these two, remember, of length LSP of I minus 1 were equal. So if this was the same as this, then this suffix will also be a suffix here. So I will also have some suffix which is going to be equal to this one and of course equal to this one. This is interesting. So as you can see, I have to look for a substring which is a suffix and also a prefix in the prefix of length LSP of I minus 1 from the pattern string. So the real question is, what is the longest substring which is a suffix and the prefix in this prefix? So the longest suffix prefix of a prefix of pattern, so definitely should be in this array, and that prefix is of length LSP of I minus 1, which means that it's from 0 to LSP of I minus 1 everything minus 1. So just as a recap, we have first tried LSP of I minus 1, and it didn't work because these two were different. And now we have found out that the best candidate is LSP of I minus 1 minus 1. If we denote this length by an integer k, and suppose that again this won't work, right? So even if this is a prefix here and a suffix here, let's say this character was c. So these two are different. LSP of I minus 1 won't be equal to k plus 1. Well, what do I need to do? Of course, there could be some even shorter suffix that ends in I minus 1, which is also a prefix here, and maybe this next character is going to be equal to a b. So again, I need to find the longest suffix from here, which is a prefix here. And remember, these two were equal. If these two are equal, this is not only a suffix here, but also a suffix here. So what do I need to do? These two are going to be equal. I need to find the LSP, longest suffix prefix, of the prefix from the pattern string, which has a length of k. So I will do LSP of k minus 1. Check if the next characters are equal. If they are, LSP of I will be this value plus 1. If not, guess what? I will go again, and if I denote this by, let's say, k prime, I'm gonna take a look at LSP of k prime minus 1 now, and so on and so forth. We will recursively do an LSP of our candidate until we either find the solution or this LSP becomes 0. Let's take a look at the code and also at some specific example. And this is how the code looks like. First of all, I initialize LSP of 0 with 0. Then I compute all the other values in the LSP. So what do I do when I compute LSP of I is that, as we've said, we are going to try out first LSP of I minus 1. And while this len is greater than 0 and pattern of len, which is the next character in that prefix, is not what I'm looking for, which is pattern of I, as we've seen, we are going to move recursively to the next LSP. So len becomes LSP of len minus 1. And we do this until we find a good match. Now, when this while loop finishes execution, it is either because len became equal to 0 or because these two are equal. So what I need to do is check if they are indeed equal, and if they are, I will increment the len, and in the end LSP of I becomes equal to len. I've chosen yet another example to really showcase how the algorithm works, because I know it is not easy to understand. So LSP of 0 equals 0. Now, I have to compute LSP of 1. What do I do? Len is first LSP of I minus 1, which is 0. So I don't even execute the while loop, and I check. Is pattern of len, pattern of 0, a, equal to pattern of I? And it is. I'm going to increment the len becomes 1, and I conclude that LSP of I equals 1, which is indeed what I'm looking for. A suffix of length 1, which is also a prefix. So this LSP is 1. Then I move on, and I want to compute LSP of 2. What do I do? Well, len is the previous LSP, which is 1, which means that this one is equal to this one. Len is greater than 0, so I check. Is this character equal to the next one, pattern of 1? Because maybe, who knows, AC was equal to AA. But unfortunately, it's not. So what I'm gonna do, len becomes LSP of len minus 1, which is LSP of 0. So LSP of 0 equals 0, len becomes 0. Then when I try to go one more time, len is 0, finish execution. I check one more time to make sure, is pattern of 0, this A, equal to this C? Maybe I have a suffix and a prefix of length 1, and they are not equal. So len is still 0, and LSP of I is 0. Then I move to the next I. I want to compute this LSP. I start with len equals LSP of I minus 1, so I start with 0. I don't even execute the while loop. I check, is pattern of len, which is pattern of 0, this A, equal to pattern of I? And they are. So at least I have a suffix of length 1, which is also a prefix. Awesome. So I increment the len becomes 1, and I set the LSP to be equal to 1. Cool. Then I move on and try to compute the next value of LSP, which is this one. Len equals LSP of I minus 1, so len is 1. I know that this one is equal to this one. So what do? Of course, I enter the while loop, and I check, is pattern of 1 different than pattern of I? Well, A and A, they are not different. Awesome. So I finish execution right away. I check to make sure, are they equal? A and A, they are equal. Okay, so I have a suffix of length 2, which is also a prefix. Increment the len becomes 2, and the SLP is now 2. Then I move to the next one and try to compute its LSP. The next one is B. So len is initially 2, len is greater than 0, and while this character is different than pattern of len, which is pattern of 2, this one, and they are different, I'm going to try out LSP of len minus 1. So LSP of 1. What is LSP of 1? It is 1. Okay, so I'm going to try out this one. With its corresponding suffix, maybe the next characters are equal. And as long as pattern of len, which is now 1, A, is different than pattern of I, it is indeed different, so this is also not good. I move to LSP of len minus 1, which is LSP of 0, which is 0, so len became 0. The while loop will finish execution. I check, is at least pattern of 0 equal to pattern of I? It's not, len stays 0 and the LSP is 0. I move on and want to compute this LSP. Len equals LSP of 5, which is 0. This is not going to be executed, so I still check if this pattern of 0 equals pattern of I, and they do, so len becomes 1, the LSP is 1, which is right, because A equals A. Now, I move to the next one, which will be here, and I first initialize len with 1. Cool. Len is greater than 0. It is. Is pattern of 1 different than pattern of I? It's not. Okay. Nice. So, again, check this. Len is incremented. So LSP of I is LSP of I minus 1 plus 1 in this scenario. We can extend. And the value here is going to be equal to 2. And I move on and compute the next LSP, which is here. Cool. What do? Len equals 2. Good. Len is greater than 0. Yes. Is pattern of 2, which is this one, different than pattern of I? It's not. Okay, so I can even extend one more time. They are equal. Len becomes 3, and the LSP is going to be equal to 3. Move to the next one. So I compute this LSP. Len is initially equal to 3. Okay. Len greater than 0. Yes. Pattern of 3, which is this one, is different than pattern of I? It's not. Okay, so I can extend even one more time. They are equal. Len is equal to 4, and the LSP becomes 4. And I move on, and I want to compute the next LSP, which is here. Len is equal to 4 initially. 4 is greater than 0. Is pattern of 4 0, 1, 2, 3, 4, this one, distinct than mine? No, it's not. Awesome. They are equal. I can extend even one more time. So as you can see, AACAA is equal to AACAA. So this SLP is now 5. And I move on and I want to compute the next and the final LSP. What do? Len will be initially equal to 5. So basically this means this suffix of len 5 with this prefix of len 5. Cool. 5 greater than 0. Yes. Pattern of 5, this one, is different than pattern of I? It is. Okay. So len becomes LSP of len minus 1, LSP of 4, which is equal to 2. So what does this mean? Is that I still have this prefix of length 2, which is also equal to a suffix here of length 2. Cool. And I take a look. Len greater than 0? Yes. Pattern of 2, which is this C, is different than A? Yes, it is. Okay, so I can't even do this, the suffix and prefix of length 3. So what am I going to do? Len will become LSP of 1, which you can see is 1. So I still try out this prefix of length 1 with this suffix of length 1. Len is greater than 0, it is. Pattern of 1, A. Is it different than pattern of I? And this time it's not. Alright. I get out of the while loop. I check one more time to be sure. Is this one equal to this one? Yes. So I increment the len. Len is now equal to 2. And of course the LSP will become 2. So as you can see in this final LSP, I've actually had to move 2 times through the LSPs until I found a valid solution. And this is it, guys. This is how we compute the LSP. Now let's see how to use it in the KMP algorithm. Alright, and finally the big moment. This is the code for the KMP algorithm. So we start with our answer, which is initially empty. then we compute the LSP, so we have the LSP array, and then we will use a variable len, which will store for us the length of the longest suffix that ends in position I, the suffix of the text string that ends in position I, such that that suffix is also a prefix in the pattern string. It is very similar to how we have computed the LSP. I know it is a little bit different than how we explained it initially, but that explanation was good for start because we didn't know about LSP, right? So what we are going to do is we are going to try out each index I from 0 to m-1, and we are going to see if the substring that ends on position I and has length m is equal to our pattern string. This is how we do it, right? And of course, if we are able to always know the len variable, which is again the length of the longest suffix that is also a prefix in pattern string, which ends at position I in the text string, then of course, if that len is equal to m, that means we have an answer. And if we have an answer, we are going to push its start index. So if the end index is I and it has a length m, we will push I minus m plus 1. So let's see how to always update the len variable whenever we move to a new I. On each iteration inside the for loop, initially in the variable len, I know the length of the longest suffix, which is also a prefix in pattern, but that ends in I minus 1, so in the previous position, right? So I do the same as on the LSP algorithm. While the len is greater than 0, and the next character, so pattern of len, is different than the character we are looking for, text of I, then of course I move one more time into the LSP. Len becomes LSP of len minus 1. In the end, after we finish the for loop, we check to be sure if pattern of len equals text of I, then we increment the len, and then that's it. We make this checking, and in the end, we return the answer. So again, just to make sure that you understand how this works, whenever we are at position I and we want to update the value of len, we know the len for the previous I. So we know what is the length of the longest suffix that ends in I minus 1, let's say is this one, that is also a prefix in the pattern string. And the line of thought is the same as in the LSP. Of course, in the best case scenario, I find that the next character here in pattern is equal to this one. Let's say this is A and this is also an A. So I can just increment the len, right? I can extend this by one character. But they might not be equal, right? Let's say this was a B. So in this case, it is probable that I have a shortest suffix that ends in I minus 1, which will be also a prefix here, and maybe that next character is going to be an A. And in order to find the length of this, I'm going to use LSP of len minus 1. If this is also not correct, and let's say this here is a B, of course, probably we have a shorter suffix here, which is a shorter prefix here, which we are going to find by taking the value of LSP of that length and so on and so forth, until we finally find two matching characters, and we can increment the length. So we have found that length, which might be equal to m, and if so, this is definitely a solution. This is a substring that is equal to the pattern one and ends on position I in the text string, and we will update the answer. And that's it, guys. Now, I know this lesson is super information heavy. Don't worry, don't get afraid, just please make sure you understand it, and in the next videos we are going to find out about the time complexity. Yes, the time complexity is big O of n, otherwise we wouldn't have discussed about the algorithm, but it is not so simple to prove it. So, I'll see you on the next ones.